Associate Program Manager for Wildfire at NASA headquarters. Excelsior is aspiring to establish an innovating and modern center of excellence for Earth surveillance and space-based monitoring of the environment. And we could not be prouder that this will be done with the advice and guidance of experts from leading worldwide institutions in space technology like NASA. Much more, we feel honored by the university for linking Excelsior project with the 10-year anniversary celebrations since its establishment. And we consider this to be a great opportunity to thank the rector and his team for vehemently and practically supporting research and innovation activities. And it is because of that support, as well as the support of the local entities and stakeholders, that the Eratosthenis Center of Excellence will enter a new era with the full support from the university in order to create an inspiring environment for further research on Earth observation and remote sensing through space technologies. Therefore, I would like to invite the rector of our university, Professor Andreas Anagiotos, to give his welcome address.
Good evening, everybody. Dear Vincent, dear colleagues, ladies and gentlemen, it is a great pleasure for me to welcome you all to Cyprus University of Technology, hosting today an interesting talk by Dr. Vincent Ambrosia in the framework of the Excelsior European Research Program. Dr. Ambrosia is a distinguished scientist in the area of Earth observation, and he is currently the NASA Applied Science Associate Program Manager for Wildland Fire at NASA headquarters, responsible for management of a portfolio of Earth observation projects in support of wildland fire management. We're very pleased that Dr. Ambrosia is a member of the External Advisory Committee for the proposed Excelsior Center of Excellence for Earth Surveillance and Space-Based Monitoring of the Environment. Taking the opportunity of today's talk, I would like to stress the importance of the Excelsior teaming project and the relevant remote sensing research conducted by our university. The scientific areas of Earth surveillance and space-based monitoring of the environment are one of the top priorities in our university's research agenda. Environment has been recognized by the Smart Specialization Strategy of Cyprus as the first horizontal priority for future growth in our country. For the last 10 years, the Remote Sensing Research Group at our university has been delivering high-quality research and services at the national and European level. For this specific area, we have acquired a critical mass of high-caliber researchers. We have developed the infrastructure to conduct state-of-the-art Earth observation research and have secured a significant amount of research funding to support our research through the Remote Sensing Laboratory at first, and now through the Eratosthenis Research Unit with a series of local and European-funded research grants. And for this, I would like to thank Dr. Hadjimitsis for his significant efforts. Given the economic scale and the restricted national funding, we believe that our efforts to promote excellence in Earth surveillance and space-based monitoring of the environment will grow in the future. The establishment of an independent center of excellence for Earth surveillance and space-based monitoring of the environment through the Excelsior Horizon 2020 teaming project will assist in resolving important issues in areas of particular interest to the region, such as maritime activities, cultural heritage, and tourism. The university's commitment to these priorities is an integral part of our research strategy. Concluding, I would like to thank you all for being here tonight. I would like to thank Dr. Ambrosia for his long-time support for several of our projects, and we're looking forward to your talk. Thank you.
On behalf of Excelsior, the project coordinator and vice rector for academic affairs, Professor Diophantos Hatzimitsis, will also say a few words on the occasion.
Dear Vincent, distinguished guests, ladies and gentlemen, on behalf of the Excelsior Horizon 2020 project, I would like to express a very warm welcome to Dr. Vincent Ambrosia from NASA to the Cyprus University of Technology premises on the opportunity of the celebration of the 10 years since our establishment. I would like to express my gratitude and appreciation to Dr. Ambrosia for accepting the invitation from the Excelsior team to join our advisory committee and provide us his advice in the preparation of the second stage proposal. The Radoseni Center of Excellence will be established during phase 2 with expertise and infrastructure could constitute a hub for Earth observation activities in the Eastern Mediterranean region. By the first 3 months of 2019, we are expecting the results of the team call. I am more than confident that the Excelsior project will be one of the successful proposals in the second stage, and Dr. Ambrosia will be a Cypriot citizen for the next 15 years. Taking this opportunity, I would like, on behalf of the team, and especially from the Cyprus University of Technology, to extend my sincere thanks to Dr. Ambrosia and NASA for supporting our activities. Thank you very much.
Our expert advisor, Dr. Vincent Ambrosia, is the NASA Applied Science Associate Program Manager for Wildland Fire at NASA headquarters, responsible for Earth observation projects in support of wildland fire management. Inter alia, he co-chairs the NASA U.S. Forest Service Tactical Fire Remote Sensing Advisory Committee since 2003. He has received various awards on wildfire observations and the NASA Outstanding Public Service Medal for his efforts on emergency wildfire observations with unmanned vehicle systems and sensors. He holds a position in the External Advisory Committee of Excelsior. I would like to call him on the floor and deliver his talk on NASA mission Earth observations. Thank you.
Thank you for the introductions. I would also like to thank the rector and the 2 vice rectors of CUT for inviting me on this prestigious occasion of the 10th anniversary of the celebration of the founding of the university here, and also the 10th anniversary of our colleagues that I've been working with for the last few years on remote sensing activities within the university. This is my 4th trip now to Cyprus, and it becomes long trips for me because I live in California, so it's a 10-hour difference for me, 10 time zone difference for me to travel here. So as I'm getting adjusted to the time zone, I now have to return back to California tomorrow. So hopefully I'll make it through the rest of the evening, still standing and not fall asleep. So what I want to talk about today is give you a little perspective on NASA and our Earth Science program. As was mentioned, I work for the Applied Science program, which is an element of the Earth Science Mission Directorate at NASA headquarters. In my role in the Applied Science program, I manage a number of portfolios, including Earth observations for wildfire interaction or wildfire observations in support of our fire management agencies in the United States, but throughout the world as well in the globe. And I'll have some examples of that. I'll also have examples of some of our other activities at NASA, including our research activities, our flight operations activities, which is our orbital and suborbital resources that we put to use to study the Earth system and to then utilize the results from those studies and that research to lead to applications development where we mature the capabilities to infuse them into our operational partners and entities, other government agencies within the United States, and share with other nations as well to improve their operational capabilities in utilizing Earth science information. And I'll provide you with some examples of some of that applications development that's gone on within the agency throughout the world and in the United States obviously as well. I'll also talk about our satellite platforms and our research component as well. So basically 4 major components within NASA that I'll be speaking about. To give you a little start, NASA actually was established as a distinctly civilian agency, and we are not associated with the Department of Defense or the military. We're a distinctly civilian agency. All of our data and information from our Earth science component is all free and open access to the public. We do not have any secrets, except for the aliens. But, but other than that, all our information is open and free access to the community. So with that, NASA was originally established in 1958, and it was an expansion or an offshoot of the original Committee on Aeronautics. So it was the National Advisory Committee on Aeronautics, NACA, N-A-C-A, that was started about near the end of World War I as an agency to look at the improving aerodynamic systems for new designs for airplane, wings, and the like. By 1958, we obviously expanded into Earth observations with satellite launches. So the agency was changed over in name to the National Aeronautics and Space Administration to represent the changes in our business profile through the decades since its founding in about 1918 as NACA. The NASA has about four major components that they conduct work in, as you'll see up there: aeronautics research, human exploration and operation, space technology and science includes Earth, solar systems, and universe. So we sit within, the Earth science community sits within the Science Mission Directorate. The other components, as you see, aeronautics, I mentioned that, and the activities that we do in high-speed aeronautics, wing design, and the like. Within human exploration, that's the operation of the International Space Station and other components of space travel that we plan for the near future, either return to the moon and to Mars. And then space technology is a development of new technologies in line with the new rocket development, new transportation systems for space travel, and then, of course, the Science Mission Directorate that I'll speak about today. Within the Science Mission Directorate, we have basically 5 major components: the Earth Science component, which I'll talk about, the Heliospheric Division, Planetary Science, our study of other planets, Astrophysics Division, which is the study of our star systems, and the Joint Agency Satellite Division, which collaborates with international agencies such as DLR, the European Union, and other agencies, JAXA in Japan, to design new mission configurations and flight operations on board satellite platforms for travel to our space station, our International Space Station, and other science research or aircraft and satellite research that goes on throughout the world. So why do we study Earth? Why does NASA study Earth? Sometimes we get asked by our more conservative administrators or political appointees in office, why is NASA doing Earth science? Well, it's one of the 4 basic tenets or 5 basic tenets that you can see that are a component of NASA. When we were established in 1958, one of our driving focus areas was on the study of our own Earth system. If we don't know enough about our own Earth system and how life can sustain itself on Earth, how can we ever study how life can be contained on another planet? So we need to know as much as we can about our own Earth system. So that has led us into the Earth Science Division and our research components and our satellite observation systems, and then our exchange of information with the international community to show how our life on Earth is affected by various changes to our landscape, whether it be climatic changes, environmental changes, and the like, to make an improved understanding of our total Earth system and how all the interactions between the atmosphere, the land, and the water take place, so we can understand the perturbations in that system affect everything on Earth. As you can see in the diagram, we call it the Gaia system. So you basically, everything is interacted together, the Earth system, the atmospheric system, and the water system. To basically allow us to monitor our planet system, we have to monitor every one of these features, and that's some of the component of the Earth science research. We have research going on in the cryosphere. We have research going on in ocean research, ocean temperature research, and the like, Earth system science, and obviously atmospheric science as well. To give you an importance of, and I can't read it really well here, so I'll focus on the screen a little bit, the importance of Earth information is critical to thriving on our planet. Helping our planet, helping plan our day. About 300 billion weather forecasts are used by just Americans every single year. 300 billion. So imagine expanding that to the world. Where's all this information come from? From the satellite information that's launched by partners in the European Union, partners in Japan, by us in the United States, that weather information. About 100 million American adults use internet-based mapping services every year. That's an amazing number, but all of those internet mapping services are provided by Earth-observing satellite systems, global positioning satellite systems designed within our agency and our partner agencies. Let's look at the use of Earth information for protecting our health. About 6.5 million premature deaths from air pollution around the world every year. This is why we study health and air quality issues on our planet, why we study atmospheric concentrations, why we monitor our planet for potential for other diseases as well that tend to affect our populations throughout the world. I'll shoot over to the keeping us secure. Estimate value of NASA and NOAA information, our partner agency, the National Oceanic and Atmospheric Administration, who also have satellite capabilities and also perform as our sister agency in Earth Science Studies, have a value. The Navy, U.S. Navy operationally allocates about $2 billion per year in procuring NASA services and NASA data to keep their information content up to protect the United States alone and throughout the world, obviously. Natural disasters, extreme weather and fires, one of my primary focuses, have cost just the U.S. federal government more than $350 billion over the past decade. If we can get improved information on these disasters, earlier assessment of disasters as precursors, and early observations of these disaster events, we can probably cut the number down on what the government spends in recovery operations and what they spend in emergency operations, fighting these disasters or protecting citizens from further expansion of the disaster events. And then enduring resource availability. Advanced technology, including many types of Earth information, will unlock up to $1.6 trillion in economic savings for energy production and use by 2035. So, very critical indications of the use of Earth observation just within the United States and somewhat throughout the world. So take those numbers and multiply them by the other agencies and the other countries throughout the world, and you can really see the importance of Earth observation data. That's why we study the Earth as a planetary system, as our living, breathing Earth system, to learn its perturbations and changes so that we can make effective decisions on how to sustain life on our own planet. As I said, the NASA Earth Science Division has 4 major focus. The research and analysis component, let's see if I get the button right, research and analysis component, the flight operations, which aren't just necessarily airborne flight, they're actually focused on space flight operations. So all of our satellites that are in orbit, collecting data, including the International Space Station. There's a technology component, which is the development of new sensor technologies, new geographic information system technologies to handle Earth science information, new telecommunications concepts to relay and to share information from the orbiting platforms and our airborne platforms to the ground and to the community in near real time for supporting our research efforts. And then, of course, the applied sciences component, which I'm a part of. So the applied sciences driving force is to take what we like to call the low-hanging fruit off of the research, flight, and technology components and bring them to our partners. And there are capabilities that are at fairly high maturity levels, technology maturity levels, so that we can integrate them into the use of our partner agencies that are mandated to protect and observe and manage our lands and water resources throughout the United States. So like the Department of Agriculture in the United States that make use of all of our technology, we take them as hand-holding partners and take some of the technologies and bring them into operational fruition through our applied science program. And that gives a nice demonstration and transfers a lot of the technology capabilities into operational use by our partners. And we do this through funding mechanisms with universities and with NASA centers and with other agencies to fund them to mature the capabilities that are derived from the earth science research component and the flight and technology component, to bring those capabilities into a much higher level of TRL, technology readiness level, or in our case, an applications readiness level, to allow us to operationally use earth science information in our various fields and our various agencies. I'm going to focus first on the flight capability, since that's the workhorse of all of our data collections that allow us to do the research and do the applied science, the flight capability. So this just gives you a good idea. This is from the Suomi National Polar Orbiting Partnership Program. It's a joint operation between NASA and the National Oceanic and Atmospheric Administration, NOAA, to increase our use of kind of moderate scale or moderate scale resolution data of the world on a global scale to look at various Earth processes. So it allows us to get a complete view of our planet each day with multiple overpasses each day over all the regions of the globe. Allows us to create this beautiful image of the Earth as the one shown here. While it might be simple, it's actually a rather complex process of adjoining and quilting, so to speak, all this information into one global image. This image was taken as the Earth looking from space on October 14, 2015. It was a day that the contiguous United States had the most clear skies. So it gives you just a kind of a world perspective. And that's from one of our latest satellite series, the NOAA, NPP, Suomi, VIIRS data, Visible Infrared Imaging Radiometer Suite. It's at a resolution, spatial resolution of anywhere between 375 meters and 750 meters coverage on the ground, and daily operates in a polar orbit and collects information on two different satellite platforms, on one platform about twice a day. So complete global coverage once a day to twice a day over the entire sphere of the Earth. That is coupled in with a number of other satellite systems, and I won't get into all of these, but you can see we have about 24 operating sensor systems that are on board a number of different platforms. Many of our platforms, our satellite observation platforms, have 2 or 3 different sensor systems on board to give us various perspectives on either the water environment or the Earth's surface environment. Some of the satellite systems you'll see are in specific flight patterns that are trailing one another, such as the Aqua, CloudSat, Calypso, Aura, Grace, and Jason-2, and Terra are in what we call the A train. So it's the AM data overpass collection time in the morning, 9:15 in the morning, equatorial pass, 9:30 in the morning, equatorial pass, and it provides us a series of satellites that are all in line with each other, making separate measurements over the same exact path. So you might have data collections from each of these platforms collecting different spectral information or gravity field information, all within a few seconds of each other, tracking down over the globe. And then you see our other satellite platforms that are listed up there, and we have quite a few of them, as I said, and their expected lifetimes are listed in there, or their potential launch dates for upcoming satellites, such as Landsat 9, which is our continuation of the Landsat series, which actually started in 1972. Kind of our first early program, our satellite program, to look at the Earth's landscape system started in 1972, and we're now focusing on the design and development and launch of the next in the series, which is Landsat 9. So we've had a series of 8 satellites that have operated in space. Currently, we have 2 of those series, 7 and 8, that are currently operating and supplying us with Earth resource information on a daily basis. Some of the others that I don't see up here, let's see, I don't have, the instruments. We have a number of Earth observation instruments that we fly on the International Space Station. And a lot of those instruments are testbed instruments that we launch to space, to the space station, to provide us with new testbed information on the potential for their operations on satellite platforms maybe a few years down the line. So we do have a series of observations from the International Space Station. And the nice thing about using the space station, obviously, is we can develop an instrument with fairly recent and new technology and launch it to the International Space Station and have it operated for a test bed period of 1 or 2 years before we design a final configuration that goes to space. And you might imagine that to design and plan and launch and operate a major satellite system going to space takes us anywhere from 3 to 8 or 9 years from conception to launch. So a lot of times, you know, we can mature some of our early stage technologies on the International Space Station. This is another video kind of showing the Earth observing satellites that monitor our planet from a unique vantage point in orbit. And all of these are primarily in polar orbits. They're not the equatorial or geostationary orbits that stare at the Earth. They come over the poles and make repeat passes over the Earth in a continuous cycle. And you'll see some of those that are in the A train that are backing up on one another. Calypso, CloudSat, Aura. So those are the A train satellites, as I mentioned earlier, that provide different types of data collection information within a train environment where they're constantly monitoring right behind each other, so you get basically simultaneous observations of the same feature in space on the Earth's surface, all within a minute or so of each other. As part of our what we want to call our flight program, we also have the traditional flight program, the Airborne Science Fleet. We operate a number of aircraft. These are the primary aircraft we operate for the agency that take scientific measurements with the same or similar sensor systems to our on our satellite platforms and provide that underflight capability to give us improved resolution, either spatially on the ground, or to give us improved temporal resolution where we can look at features continuously rather than waiting for an orbital overpass from a satellite. So they also provide us with the calibration capabilities to calibrate our observations from space with our observations from these airborne platforms as well. The other advantage they provide us is with a lot of these high altitude airplanes, we can also replicate what we're going to see from space through that atmospheric column. So with these high altitude airplanes, we're above 99% of the Earth's atmosphere. So that provides us almost a satellite look where we're looking completely through the atmospheric column, can make measurements of that atmospheric column and see how much that atmospheric column does distort the response signal from the satellite, the imaging satellite. And so it provides us with a calibration coefficient to allow us to make improved assessments and improved measurements that are more highly calibrated from our satellite platforms based upon these observations from our airborne platforms. A couple of ones that I want to point out up here in the upper left. This is the NASA Global Hawk. We have 3 Global Hawks, which are unmanned vehicle systems capable of operations at about 70,000 feet, so 22 kilometers altitude, and have flight endurance of 32 hours. So we can fly these about 14,000 nautical miles, allowing us to make long-term measurements and long-term observations from an unmanned aircraft loaded with instrumentation. This is a fairly large aircraft, about the size, a little bit smaller than an Airbus. What's the smallest Airbus? Airbus 320, is it still smallest? So a little bit smaller than that, but with a significant payload capability, which is located throughout a number of different panels here and in the nose configuration. The top fuselage of the aircraft has is a radome and has a satellite dish in there, so we do throughout the globe satellite communications for the data relay and operations of the platform from NASA in a couple of different facilities. We can operate the flight operations of this platform, but it can be flying anywhere in the globe with a control stick in the hands of a pilot in Southern California. So a real workhorse for our agency now, more recently. And then the Tana aircraft, which is a military Predator B aircraft that's been completely stripped of all the military operations or options of it, and has been installed with a number of different payload capabilities in the nose and in the sensor wing. This was the aircraft that I was the primary science investigator on when we flew a number of wildfire missions, observing wildfires in the western United States in 2006 through 2009, and then relaying the information from this platform to the ground in real time to the incident command centers to make effective use of the information, the scenes that we were collecting, and then to put those into operational utility to enable them to manage the fire more effectively. We operated that mission for about 3 years, as I said, as a demonstration with our partners on these emerging technologies like UAVs, automated sensor systems, automated onboard processing, and automated relay of the information to various points on the ground. So we were turning around data. Oops, let me go back. We were turning, am I going the right way? Come on. Okay. So we were operating the sensor on board this aircraft remotely, and it was basically an autonomous operation with the sensor working on its own, providing products that were geo-rectified to the Earth's surface on every pixel basis. So you come out with a geo-rectified image of the Earth's surface with the fires indicated on it, all within 3 minutes, 2 to 3 minutes of it being collected on the aircraft in a map-based format. So we were doing all of our processing on board that aircraft automatically to derive the spectral channels we wanted, and then to do the marrying of that spectral information with the digital elevation data that was flying on board that was actually collected from the shuttle topographic mapping mission a few years ago that provides us with topographic information of the entire globe. So doing complete geo-rectification of the data on the fly and transmitting the data to incident commanders on the ground. Much like you'd expect the military to have capabilities of very similar to that, but for civilian use and fighting fires in this case. That platform is capable of about 24 hours of operation and about an altitude of 40,000 feet. We generally fly this at about 18,000 feet, which is about 6 kilometers, a little bit less than 6 kilometers, 5.5 kilometers up, to give us good perspectives and good sensor coverage over wildfire events and other features on the Earth. Some of these other platforms, a workhorse that's been within the agency for a very long time is the NASA ER-2. Again, a Lockheed aircraft that was originally designed as a spy plane for the military back in 1956. You might remember, maybe you don't, the U.S. had one of these aircraft shut down over Russia. Gary Powers, the pilot, bailed out of the aircraft and was captured by the Russians and held by the Russians for a series of months before an exchange was arranged between the United States and Russia, exchanging some of the spies that we had in the United States for Gary Powers, who was the pilot in this in that particular aircraft. So that aircraft is used by NASA. They're still operated within the military. There are still aircraft like this operated in the military, but NASA has their own aircraft, has 2 of these aircraft to do earth science studies. Again, a high altitude platform, piloted though, capabilities of about 65,000, 70,000 feet, so again, 22 kilometers up, and about durations of 8 hours, give or take. So very nice platform, again, to test bed some of our other sensor systems and to collect data for Earth observation studies. The large platform here is a DC-8, and that's our flying atmospheric observatory that we can load up with a number of different instruments because of the large payload capability of that aircraft to fly atmospheric sampling missions primarily in support of our other Earth science elements. And then some of the smaller, this is the Gulfstream aircraft that's used for a synthetic aperture radar mission program that we've got operating in primarily out of NASA Jet Propulsion Laboratory in Southern California to look at distortions in the Earth's surface from the UAV SAR, the synthetic aperture radar, and other mission or science mission profiles. Aircraft in the middle is a moderate-sized UAV. It is the Sierra aircraft, and it is about a 12-hour unmanned vehicle system, and it has a payload of about 75 pounds. What would that be? 30, give or take, 30, pardon me? Anyway, 75 pounds for us in the U.S. And so a moderate-sized payload capability, unmanned vehicle system, and we have flown this on numerous missions up in the Arctic and in Svalbard, Norway as well, to do some sea ice mapping inventories from us on a kind of smaller scale. So you can see our fleet is fairly significant and deep. This aircraft up here is a P-3, again, an airborne atmospheric observatory where we can have a number of different scientists and their instruments on board, all collecting information on the atmospheric, the troposphere, solar radiance measurements, and the like. Let's move to the research component now. And I think what I've got here is a few, this is not going to show up really well. It's a little bit too dark. But it basically shows the biosphere on a yearly cycle. And I apologize for this. I thought it looked better when we had it going earlier. But anyways, it's again a composite of the land and plant life on the land and in the water. So what you're seeing in the oceans are the changes in the organisms, phytoplankton organisms, that are captured from specific wavelengths on this sensor system. So this again is derived from the MODIS observations, which is a moderate resolution, about a 750 to 1,000, there we go, about 1,000 meter resolution, covering the globe during a seasonal period. And this is basically showing from December to February during these diurnal cycle, or yearly cycles in, again, you can see the creeping of the ice during the winter, northern hemisphere period, the change in, let's see if I can do this and get it rerunning again. And you can see the biomass buildup, and especially here in Africa, the change in the sub-Saharan vegetation composition. So this is biomass. This again is chlorophyll concentrations in the ocean. You can see it along the El Nino currents here, and the northern hemisphere, northern Pacific, and northern Atlantic. And it's the earth breathing, basically. It's the earth and the vegetation on the land surface and in the waters actually breathing to produce this view of the earth as a complete system with the changing dynamics of the Earth's surface biosphere, the plant greening up and the plants going into their winter dormant periods, and of course the changes in the ocean profiles for phytoplankton and the like. Here's another one that's near and dear to me. This is a global fire tour, and it basically shows the same satellite information from the MODIS satellite information that provides us characteristics in a number of different spectral bands that are really important to visualizing hot source temperatures like wildfires. In the mid-wave infrared region, we can get a very good, accurate profile of wildfires throughout the world from the MODIS sensor. So this shows you a composite that was developed for the whole globe over a 1-year period. Actually, it's from a 9-year period, from July 2002 through July 2011. And you can see as we move through these various continents, again, the greening up and the browning out, and as you see the browning out heading into drying season in the sub-Sahel region, you see a lot of the fire stars. And then the constant kind of fire configuration over equatorial Africa during the majority of the year. Again, here's Brazil and South America, and you'll see a number of fires in Brazil and in the Amazon region. A lot of those are man-caused fires for land clearing operations. Here's the United States. You can see during our winter period, the snow accumulation, but then you see a number of different fires that are actually agricultural fires in the central part of the United States. They're not the wildfire environments, they're agricultural fires. And if we had continued it farther into the year, we end here in July, but about July is when we get the fires in the western United States. Here's California, that really crop up in our forest land environments and in our Mediterranean ecosystems like California from the fire period of about July through September, October, and into November. This next graphic, if hope it plays, oh good, it's playing really well. So this is again a composite of a number of different earth science scenes. This covers, this is a GOES-5 simulation. So GOES-5 is a production development at NASA Goddard that that basically covers a simulation covering 2 years from May 2005 to May 2007. To do this kind of global aerosols development over a 2-year period, it ran on 3,750 processors on the NASA Discover supercomputer in the Center for Climate Simulation. It consumed 3 million processor hours and produced 400 terabytes of data just to do this 2-year display of the aerosols. One of the interesting things that you can see in the aerosols is, of course, the aerosols are composed of smoke from wildfires and constituents in the atmosphere from wildfires. You get a lot of the Saharan desert, dust storms, and you get also pollution concentrations from the east coast of the United States traveling over to northern Europe, and of course from China traveling over to the US from industrial development. One of the other things that's really interesting, like I said, you get smoke plume development, but this was one of the first indications that we had that we were seeing smoke plumes that were derived from fires in Canada, and as you can see following some of these circular flow patterns up to the Arctic, and basically depositing black soot, black carbon, onto the Arctic ice surface. Now what's that going to do? It's going to change the albedo of the ice surface and basically create an absorption of solar radiation rather than a reflectance, like the bright reflectance you would get off the snow. So now when you've coated that snow surface or ice surface with a black carbon matter, even at microscopic levels, you're starting to increase the absorption of solar energy to that surface, and it's causing a melting of the polar ice caps. So contributions from black carbon and other emissions from our industrial areas contribute to that as well as natural causes such as the black carbon from forest fires. But this is a wonderful simulation, and you can see as it progresses some of these beautiful storm systems and cloud pattern systems in the southern oceans, and then you can even track some of these hurricanes that are moving up the coast that come over, are carried over from the west coast of Africa into the Caribbean region and up our eastern coast of the United States. But information like this wasn't available to us 10 years ago. Another perfect example of one of the topics I was talking about, the reduction in Arctic sea ice areas. And we provide the satellite information that is the proof of sea ice decline at the northern hemisphere and also the southern hemisphere in Antarctica as well. And what you can see here is I think it's the minimum extent of Arctic sea ice since 1979 in this graph. So this is continually monitoring the surface sea ice conditions or the coverage area of sea ice throughout the season, spring and summer. And we're looking at the decline in the reduction in the area of sea ice, opening up the Northwest Passage, as you can see. And we're figuring that within about 10 to 15 years, or maybe even less, this Northwest Passage will be completely ice-free and allow, throughout the season, allow transportation to and through. You can look at this from an economic viability point if you're a shipping company to have access without having to go through the Panama Canal, or you can also look at it as an exploration potential if you're an oil or gas producing company that is very interested in some of the resources that are up here in northern Canada and in the Arctic. So, good and bad features that information like this can provide to us. And you can see the pattern of this decline in the coverage of Arctic sea ice between about 1979 and 2015, of which this graph goes to. And it's been a steady decline. So we are seeing the melting of the polar ice cap from satellite data. So this provides us the smoking gun of the changes in our landscape brought on by industrial revolution and our contributions, anthropogenic man-made contributions to global climate change. Let me jump to applied sciences, the group that I'm in. So applied sciences, as I mentioned earlier, serves as a role to advance global knowledge of effective use and extent of earth science information for important decisions and actions. So this is where we take some of our research objectives and put them into use with making decision points for our partners in other federal agencies, within the civilian community and the global community as well. So we have basically 3 different ways we look at the advantage or the use of earth science data and applications. So we integrate a lot of our applications into the mission planning. So now as we plan our new satellite systems, we always have mission application scientists on those initial design teams, not just researchers, but mission application scientists that basically say, these are the configurations of this satellite that I need to have improved information of wildfire monitoring. So we also provide societal and economic applications where we look at the benefits, the economic benefits of earth science information and relay that to the partners so that they can obviously assume that they're going to make effective use and it's going to be of societal benefit and economic benefit to the country, as I was showing you the importance on the expenditures of earth resource information on reducing some of the costs for disaster assessment and the like in the United States alone. And then building capacity. That involves our training and our education of the greater community in the use of earth science information. So it's one of the components I've talked about with our partners here in the Excelsior project to look at how we might help in building that capacity, that understanding of earth science information through workshops, webinar series. Basically, you're informing the world of the uses of earth observation, and hopefully then those get implanted into operational use within the communities. There are 4 major applications areas that we focus on: health and air quality, water resources, disasters, ecological forecasting, but we also support 5 additional areas: agricultural, climate, weather, energy, and oceans. And I'm the Associate Program Manager for the Wildland Fires, which is a cross-cutting theme, because wildland fires aren't just about disasters. They're also about health and air quality. They're also about ecological forecasting and biospheric change to the environment, and they also involve inputs to ocean systems and weather and climate, obviously. So these are the 5 major elements that within the applied science program that we focus on and working with partners. Give you a good idea of the general types of applications we work on. There is development of new applications and decision support tools with partner organizations, such as the United Nations now using Terra and Aqua satellite data to identify fires and send alerts. So this is a new application that was developed off the satellite data. But we also enhance other people's decision support systems and their operational systems by the inclusion and ingestion of earth science information or earth information. So in this case, we have basically a daily, weekly, and monthly U.S. drought monitoring system in the U.S. that covers the whole United States, and one of the capabilities that incorporates are the NASA GRACE, the gravity monitoring the Gravity Recovery and Climate Experiment that maps the Earth's gravity fields with 2 spacecraft that are flying in position, and they're separated by about 220 kilometers in a polar orbit. And based upon their separation in space, they can measure the gravity field very effectively on the Earth's surface. So it gives them an indication of where these water storage or soil moisture profiles, where there's a different gravity pattern on the Earth's surface. So where there's a loss of surface water or a loss of underwater or underground storage capacity of underground systems, you'll see this configuration of the change in the gravity field, which allows us to predict the lack of water in these large regions of the United States, especially for agricultural production. So an interesting use of a non-imaging satellite system that's basically looking at gravity fields, giving us information about the amount of water on the surface or in subsurface aquifers. So that's a nice demonstration of the capabilities of spinning off research capabilities into applicable uses with the community to improve agricultural efficiency and water distribution. Disaster response and recovery, that was a major component of our applied science, and it's basically to help the global community in providing resource information from our satellite observations on how to make effective and faster decision management support. Maybe it's recovery operations, maybe in the case of fires, it's pre-fire condition and vegetation stress, to give an indication of where fires might start. But you can see the importance of the use of Earth observation tools from this satellite perspective above to give us a good feel on the distribution of disaster events throughout the world. This is, in particular, is about the Deepwater Horizon oil spill and the various satellite data that was collected over it, various mapping tools and satellite data to show the spill and the movement of the spill through the Gulf and potentially out into the Atlantic. Another example where we provide key partnership and end-to-end response is, again, in disasters, remote sensing of floods with our observation capabilities and our fairly high-resolution satellite data sets that can be modeled to show regions of inundation during major floods in the United States or throughout the world. So providing this information in near real time to our partners in the emergency management community and then the international community as well. We support the international community with requests that come in from the International Disaster Charter with NASA data to provide them with fairly near real time, if we can, information on various events throughout the globe, including, I think I have it here, Hurricane Hermine from MODIS, data collection in 2016. Let me go back. No, I don't have it on this one. But we did support the Nepal earthquake with looking at earthquake damage and the distribution, regional distribution of earthquake damage from the Nepal earthquake. Was that 2016, I believe? Hurricane observations is another keen partnership we have on the integration of earth science information into operational use. So this data is used by the National Hurricane Center in the United States to basically forecast landfall and to reduce the variability in your predicted landfall location. So if you can reduce the swath width that you're predicting 6 to 8 hours in advance of where that hurricane might hit, you can reduce the amount of people that you have to remove from that community to get outside the region of impact of that hurricane event. So providing near real-time information on a repeatable basis that shows the track of the hurricane as it's coming in to make landfall to reduce the potential for loss of life caught in the storm's path. Infectious disease environmental health monitoring, looking at cyanobacteria blooms in one of our major Great Lakes in the United States, near New York. Early warning system for malaria risk in the Amazon, looking at a number of different factors, soil moisture condition, rainfall information, so a combination of a number of different satellite observations into one decision support system to predict malaria risk based upon life cycles of the malaria mosquito and also the conditions under which that life cycle is of greatest potential to expand and grow. So again, it's water availability, pooling water availability, temperature, and it could be storm movement and the like. So it's building all of these data sets together from a number of different satellite systems. This little graphic, the graphic in the center is a movie playing that shows the air quality improvements between 2005 and 2019 for NO2 emissions from our major urban areas. And you can see on these individual graphs of San Francisco Bay Area, the Chicago area, Philadelphia, New York, Atlanta, Denver, Los Angeles, Houston, and Tampa, that U.S. air quality has improved between 2005 and 2019. This is the NO2 emissions in the atmosphere from these urbanized areas. And you can see the change from one period of time over about a 6-year period. And this movie really plays it really well, showing the decline, especially in the eastern United States, on NO2 pollution and air quality improvements. So it allows us the monitoring capabilities to see that our effective decisions made by the Environmental Protection Agency are really being effectively implemented, and our use of low smog fuels for our cars, the transition from gasoline-powered to hybrid cars and electric cars really will make a play in reducing N2O emissions throughout the United States and obviously the globe. And we have a way of monitoring that. and basically relying on this type of information to say that we are making a reduction, we're seeing an improvement in our air quality. Again, this is a similar malaria risk modeling application in, where am I? I think it's Thailand. Anyways, and it's the incorporation of a number of different data sets to basically model through a decision support system the malaria risk for these regions, and it's based upon the mosquito life cycle, as I said, where they live and breed. Insecticide and other treatments can then be applied. So it's taking a number of different features, like the amount of rainfall that has fallen in the region, the pooling of water, the dry season, the growing season, combining these all into a geographic information system, a decision support system, to predict malaria risk in specific regions, to go in and take effective action either with insecticides or to help the people with malaria preventive capabilities. Wildfires, again, we run a lot of the NASA data through a number of different models to derive pre-fire burn conditions, so where we have a hazardous buildup of fuels, where we have a reduction in the biomass of fuels, or where we have a drying out of vegetation. We can monitor that and give us a good prediction on where wildfires are likely to start, from natural causes, of course, from lightning strikes and the like. We also monitor in real time wildfire events throughout the United States and provide that information to the wildfire management agencies, the United States Forest Service, and the United States Bureau of Land Management, our two major land management agencies in the country, to monitor wildfires in real time, and then utilizing the same information for post-fire management and recovery operations to be able to track with different spectral bands the regrowth potential on various burn severity ecosystems, to look at what systems need some help in recovery and new biomass plantings or the like, and what systems are recovering naturally and pretty well. As an example of that, here's where we've gone over the last few years with the improvement in spatial resolution of some of our satellite data that is used for fire detection. So this is was a major fire in California, the Rim fire, and this just shows 3 different sensor systems that collected the fire during these time periods. So this is along the A-train orbit, and so this is the MODIS sensor system, and it's at about a 1 kilometer spatial resolution. You can see it's kind of blocky information. So, you know, it could be used somewhat effectively. So the red spots are the most current fire locations, but again, it's a 1 kilometer size pixel, fairly large. The VIIRS has a visible infrared, infrared satellite suite system, has a 750 meter thermal channel on board. So you can see an improvement in the spatial quality and integrity of the data, as well as its multiple overpass configurations and slightly different time to get kind of during the height of the burning period during the day when the sun is at its highest solar elevation. So you're capturing data at a slightly different time than this overpass from MODIS, and at a much better spatial resolution. And then VIIRS also has a 375 meter channel, and you can see again the great improvement in spatial resolution. So this is really important for incident management teams to know where to deploy resources, whether it be personnel, trucks, aerial retardant bombers, and the like. And you can see where a lot of this information, maybe not so much in Europe, where you get an early indication of fire starts because you've got, you know, a dense population throughout the entire continent, but where this information is important are places like Siberia, northern Canada, parts of Africa, where you don't have that indication from the community that I see smoke or I see a fire starting. So the importance of satellite data to provide near real-time information on disaster events when they occur in low populated places or that are inaccessible to us. I'll run through some of these pretty fast so I can finish up. Ecological forecasting, one of our components is to look at the ecological influence between man and our landscape and the creatures that live on that landscape. So we do studies of habitat management as well to look at endangered species or riverine quality for our development of our salmon breeding grounds, if you will, and also in tracking whale systems with nodes on the whales to track the whales' migration routes, coupled with satellite observations of sea surface temperatures, chlorophyll concentrations, phytoplankton, and the like throughout the globe to see how their migration patterns are changing based upon our changing environment or the changing ocean environment. Temperature increases may play a role in making their migration patterns different or even in their breeding grounds. And so we need to study their ecosystems and to understand how we're affecting the plant and animal community throughout the globe. So kind of the focus of our ecological forecasting, what's going to happen in the future, giving these changing landscape considerations or changing ocean temperatures, changing biomass loads, the world getting warmer or cooler, etc. Coral reefs, another major study that is going on right now too. The world's coral reefs are actually quickly disappearing. A lot of this is due to sea surface temperature changes that's causing coral bleaching in some of these regions. Also pollution too. But if we go to this next slide, come on, maybe it'll switch to, it basically shows it's the NASA and NOAA Coral Reef Watch program, which integrates satellite data looking at sea surface temperatures on the globe. And these, you can see the effects of the El Nino, you know, the equatorial El Nino that's coming across, and as it shifts north, you know, provides warmer waters to California, changes the sea surface temperature and the storm patterns in the U.S., but it also affects the coral reefs in these regions. So when you can see the buildup of these red areas, these dangerous or hazardous areas, that's where you can expect severe coral bleaching to go on. So, of course, the Great Barrier Reef, Great Barrier Reef in Australia along here, and if we were to run this again, go through the scenario, you'll see during different times of the year where you'll get a buildup of higher sea surface temperatures from one of our satellite observations. Water resources, how to manage water in a water-limited area like the Central Valley of California, which is the breadbasket for the United States, for all of our vegetables and the like, and to make effective use of Earth observation data to look at water storage capability, look at evapotranspiration from different crops, all with time series analysis of satellite data. How do you find and use satellite data? I'm getting kind of near the end. So we have a number of different programs at NASA that educate the community on where and how to use NASA data. And so some of this might be of interest to you people, because we have a lot of online webinar series and online information sets that you can access and take the training yourself in your own free time. We also have schedules where we provide online training once a week, if you're available, for 1 hour a day. So it's basically 5 to 6 weeks of training where you can learn more about the uses of remote sensing data and how to access it. So that's what I'll talk about. A couple of the programs. The Severe program, which I'd like to get the Excelsior team involved in, is building international capacity. Currently we have hubs, and so these are for underserved regions that are not typical users of Earth observation data. East Africa, Hindu-Kush, Mesoamerica, Southeast Asia, and I'd like to see one in this region covering the Eastern Mediterranean, North Africa, and maybe some of the Balkan states, but as an underserved region. I'm trying to convince NASA that they need to link with the Excelsior program and establish a Severe Center here. The Severe Center is actually co-organized by NASA and the U.S. Agency for International Development. That's how we can collaborate internationally. Sometimes we can't naturally collaborate internationally through NASA, so we go through our partner agencies. Applied remote sensing training, that's where you get some of the hands-on experience with basic and advanced training. Those are the online tools, webinar series, and workshops. And then the develop is a workshop, local government capacity building that we do with a lot of our students. So we have students that run through the develop program and basically partner with an agency to integrate the use of Earth observation into their applicable programs. They do this over a 6 to 10 week period. I've decided, after seeing our developed students who are anywhere from high school to college level, who have no experience basically in remote sensing, come into our agency, do within 6 to 10 weeks, take a project from initial concept and idea through to applicable sharing with the partner agency. 6 to 10 weeks, I've gotten to the point where I watched them enough, I decided I need to retire because they're just blowing me away with the things that I used to have to do over a 2-year period, they're doing in 6 to 10 weeks. So our young people in the audience, I bow to you because you're our next generation that are energetic, intuitive, and are going to replace the people like me. I'm ready to retire. I basically shed a tear every time I see what they do because it amazes me. I'm over the hill now. And here's our severe nodes. As I mentioned, we have a number of projects in equatorial Africa. This is a new node in the Himalaya region and also in the Southeast Asia, excuse me. Of course, our capabilities initially started in Central America. So this is one of the capabilities I've been talking with at NASA headquarters about potentially creating a new node here. I don't know if you would be considered an underutilized region, but we'll just see how it plays out. So this program, severe program, basically, as I said, is an international program, but it's training users in the use of Earth observation for their particular needs in these specific regions. Like this is looking at frost mapping for predicting yields from the coffee crops in Kenya and the East African region. So I'll just zip through a couple of these real quick. The Applied Remote Sensing Training Program, I think I've got the website address on the next slide, but again, this is where we provide the webinar series and the workshop series to the community. We basically focus on disasters, ecosystem or ecology, health and air quality, and water resources. As I said, we do online webinars. Can you read the graphic down there? I'll leave you with these slides. It's fine for us. But basically, the online webinar series is, if you attend it during the webinar series, it's like in the US, it would be an evening time, so it might not be very convenient time-wise for people here. But they are recorded and available both live and recorded, and it includes demos on data access and the like, and everything from the basic introductory to remote sensing on through to more specific subfields like fire monitoring, use of satellite data, where to get it, etc. We also do in-person workshops held in a computer lab for 2 to 7 days. We do relevant local case studies, and we do these internationally too. And then one of the things that might be interesting for us with Excelsior is train the trainers. So courses and training materials for you guys that we work with you so that you then become the trainers on the uses of these technologies. We've done 96 trainings. We've done 11,000 participants worldwide. So get in line. Get in line, be early adapters. 2,500 organizations in over 150 countries. And you can see we get a lot of input, obviously, from US, Canada, Brazil, surprisingly, India, Bangladesh, some of the European countries, obviously. But interesting, the distribution of that map. And then develop, as I said, are the students that build capacity, both within the participants, the students involved learn a lot about the use of remote sensing, but also partner with agencies like the U.S. Forest Service to show them how to do timber type mapping with Landsat data, satellite observations, and the like. And then, how do we all do this? What drives us? Who tells us at NASA what to do? Actually, the community does, the scientific community. Every 10 years, there is a decadal survey, it's called, that is laid out by the National Academy of Sciences in the United States. And the National Academy of Sciences has a select group of world-renowned scientists that define the science issues that the agencies like NASA NOAA, the National Oceanic and Atmospheric Administration, and the U.S. Geological Survey as our Earth science component of the United States, what they need to focus on. So it's driven by the science requirements coming out of the science community, telling the agencies, these are the focus arenas for you to work on. And it's not saying, these are the kind of satellites you need. It's saying, these are the science issues that you need to focus on. Whether it's water availability, so a lot of it is global societal needs, water availability, climate change. So then the agencies are mandated to follow the guidance of these documents, and they're planned out for the next 10 years. So the latest one was just released about a week ago, covers from basically the end of 2018 through 2027. So we're just going through the document now, seeing what the requirements are that are driven by the user community. So this is not driven by the government. It's not driven by the president. It's driven by the science community in the United States. Thank God it's not driven by our president. We're not recording this in the US, are we? Is there anybody from the embassy here? Good. So these are the recommendations. Really quickly, aerosols, cloud convection, mass change, surface biology, geology, surface deformation, the coupling of water and energy cycles, ecosystems change. So these kind of high-level definitions of what the science community feels are the gaps in science knowledge. And this is not only for the U.S. We are designing these systems, of course, within the U.S., but to serve the needs of the world and the world community and the world scientists. So these are how we get our marching orders about what we'll be doing for the next 10 years. Again, there's also other documents that are produced by National Academy, and they basically say that from the community, we need a continuation of these Earth observation capabilities. So a lot of times as an agency, we'll produce a research satellite system that will fly for 3 years and then we deorbit it. The community starts to rely on these capabilities and they want to see that continuity before they make an investment in procuring that data or using that data. If I'm going to convince you to utilize a satellite sensor system for doing fire monitoring and mapping, and you're going to build a capacity to do that, build a laboratory, build a facility, build the downlink station to acquire the data and the like, and then I tell you, but wait, it's only going to be operational for 3 years and then we're going away. You're not going to rely on that platform. So there is a community that says we need to have this continuity of observations with, in some cases, repeat satellite capabilities over the years to come so that we can rely on continuous record of Earth observations from the same kind of platform suite, sensor suite resolution. And then, of course, as Cyprus does, the United States is involved in the group on Earth observations, GEO, and it is kind of the United Nations of Earth observations, where all the nations have representatives from their either their space agencies or their user community and university level to partner on deciding and utilizing the various Earth observation capabilities throughout the globe, whether it's India's satellite system, DLRs in Germany, the EUs, and the like. So there are member countries. There are 90 member countries. You can see most of the globe is covered. Africa is being covered even more now. This is about a year old. And there's a number of different partner organizations. Cyprus is part of the GEO organization, as is most of the nations in the Eastern Mediterranean, you can see. And therefore, this provides our impetus and our ability within NASA to collaborate on an international scale through this partnership effort to promote the use of Earth observations. NASA just funded a number of different efforts within the GEO within the GEO realm of capabilities, and so we are funding scientists in the United States to make a contribution to the international group on Earth observation in these specific fields. One of which, the one that I'm leading, is the Global Wildfire Information System. which is actually housed here in the EU and managed through the Joint Research Center in Ispra, Italy. So we'll be contributing our capabilities to make all of these observation throughout the world, to make those operationally useful by the international community. Last slide, or near the last slide, I think it's the second to last slide, just to give you an idea of where our budget is. I could have put this at the front, but I saved it for the last. So this is our Earth Science Division appropriation history as a percent of the NASA budget. So our Earth Science Division budget, we're right in here, we're actually in 2018, but as of 2017, our budget has stayed somewhat, declining slightly, but we're at about $2 billion a year. That, as you can imagine, is a lot of money, primarily going to satellite operations, launch services, and the like. So within the Applied Science program, we are about under a $60 million a year budget. So we're a component of this large $2 billion effort. So if you really look at it, the Earth Science Division is about a fifth, about a tenth, 10% of the NASA overall budget, which is $18.5 billion. So a fairly large component of the agency is involved in Earth science, information, data collection, and transfer to the community. Give you the importance of the decadal survey. This decadal survey that came out at this point reported that there was a lag in the nation's Earth observation satellite system was in danger of collapse. We didn't have enough resources. We weren't putting, our government, our administration was not putting enough effort or dollars into new platform launch, and we dropped down to 6% of the overall NASA budget, and our satellites, which were either being, are reaching their expiration dates for their lifespan, or new satellites were not being built. We reached our lowest point here in 2005, 2006. So the importance of the decadal survey, saying to our administration and the community, we need funds to maintain our Earth observation capabilities, both for U.S. ability and economic growth, as well as to support the world in studying the planet and our Earth system science. Closing remark. I'd like to do this because it relates to the current situation in the United States and the kind of administrative or political, not battles we're having, but in recognizing the global climate change issues. And so what we try to now tell our administration and people throughout the world is Earth observations and Earth science data are objective, transparent, and policy neutral. We don't make policy decisions. We provide the information that's calibrated, accurate, and time series to allow decision makers to make decisions on the planet, the economic viability of the planet, the viability of our ecosystems to sustain change. NASA Earth Science doesn't develop or prescribe policy. Other agencies and other organizations use our data and scientific results in their policy analysis. So we're government neutral. We don't care which party is in power in the White House or in Congress. We simply want to provide accurate, truthful, long-term information on the condition of the planet. We consider ourselves the doctors with the stethoscopes that are measuring the heartbeat of the world. During the current U.S. administration, there's a lot of speculation about NASA's direction. We as an agency, we're committed to working with industry, international, and other partners to ensure that we meet our ambitious plans for the new satellite directions and new science-driven mission objectives. And as you saw from that decadal survey, those are our marching orders, not what the administration tells us to do and not what Congress tells us to do. They can cut our funds and say, no, you're not going to abide by what this tremendously influential, Nobel Prize-winning scientific community tells you you should do. They can always cut our funds, but it becomes very difficult to do that. when we've got the backing of the science community throughout the world. And then, as I said, for all nations that are undergoing, severe budgetary restrictions, whether it's in hiring personnel, whether it's in science objectives, it behooves all of us, especially NASA and our partners at DLR and the international community here in Europe, that we work together so that we can maximize our Earth observations and collaborate effectively and efficiently, economically efficiently, on these type of Earth science objectives and our analysis of all of our global data collections. We can't do this alone, and we don't have the resources to do that alone. No country does, so it behooves us to collaborate internationally with our community. And there you go. For further information, our websites and our overall science mission directorate website is at that first one, Science NASA Gov, Earth Science, and the Applied Science has their own website where you can see some of these examples. You can see the training capabilities within our RSET program and other programs at NASA if you want to find out some more information about it. So with that, I want to thank you for staying attuned to an extended presentation that I provided. I get to talking and I can't stop because I love this stuff. I'm excited about it. I'm passionate about Earth sciences. I've been doing this at NASA since 1980. I started when I was 3 years old.
Forward to actually using some of these sophisticated tools that NASA has in the Excelsior program, and please let us know how it can possibly influence so that we can have a severe center, as you mentioned, that there is the thought of having the center here in Cyprus to help the Eastern Mediterranean. But again, thank you very, very much for being here with us today. Thank you.
Thank you very much indeed, Dr. Ambrosia. We were happy that you couldn't stop because we wanted more. So the good news is that this presentation will be uploaded on the website of Excelsior, so you can have a look. And that reminds me that I need to say that you have to follow Excelsior. The hashtag is, just a moment. Just there. So I'm going to call the rector and the vice rectors to kindly award a medal of the university to Dr. Ambrosia. And I would like to say thank you to all of you for attending this event. And you're welcome to join us for a cocktail in the lobby. Thank you.
εσύ. Όχι, το ξεχάμε, έφυγε από το χρόνο και έκανε. Μπορείς, ήθελε ο ίδιος να δεχτεί. Μπορείς να το ρωτήσεις άμα θέλεις. Ναι, όχι, κάθισε, γιατί ο ίδιος το ήθελε να το κάνει, απλώς έφυγε τώρα έτσι με το τέτοιο. Θα ευχαριστηθεί.